Hello, good morning, all. Let us now begin with our next part of real analysis. Today, we are going to see few results related to the sequences of real numbers. Let us deal with the theorem. If 0 less than x less than 1, then the sequence of x raised to n converges to 0. This we mean to say. So by this we have capital S as the sequence of real numbers which are powers of x. We have x raised to n here, and n varies from 1 to infinity. What will happen to such sequence? This we mean to see. And the condition given on x is 0 less than x means x is positive, and less than 1 means x is a fraction. So fraction raised to n we want to visualize. Very surely I would like to deal with the fraction half. So if at all I take half, all of you can observe half square becomes 1 by 4. So very immediately you are watching that half is greater than 1 by 4. Next you see 1 half cube, it is 1 by 8. It is still smaller, and so on, and still the terms are all positive, means all of them they are greater than 0. This fact we are going to use here. So let us prove it. We consider sequence as equal to curly bracket x raised to n with 0 less than x less than 1. So as I have shown here with the example, x raised to n plus 1 can be said that x into x raised to n, but x is smaller than 1. So if I multiply both sides by x raised to n, what I will get is x into x raised to n is smaller than x raised to n. What do we mean? Every next term is smaller than the previous term. So the sequence is monotone decreasing sequence. We can say the sequence is monotone decreasing sequence, or it's a non-increasing kind of sequence. Further, we know all the terms are positive, means they are greater than 0. So to the lower side it is bounded by 0. So we can observe 0 less than all the terms, less than the n plus 1th term, less than the nth term, less, and so on up to the first term, which is already less than 1. So what this means? S is bounded below. Monotone decreasing plus bounded below. So we have to use monotone convergence theorem. It says S is convergent. Now, if it is convergent, it will have some limit. What is the concept of limit? Limit means after crossing certain n, for all n's greater than certain fixed natural number, all the terms Sn are going near to the limiting value, are very well closed to the limiting value. What we mean by this? Modulus of Sn minus L, the difference between Sn minus L, Sn is the nth term, is as small as you wish. So that value particularly we denote by epsilon. So if L is the limit, will mean this Sn, then Sn plus 1, they will all be approximately equal to L. This is the meaning of the statement. So Sn is the same as Sn plus 1, which is already same as the next term, Sn plus 2, and so on. And this is true for all the terms greater than n. So all those terms, they are approximately equal, this we mean to say. So L is the limit means what? These values all will be as equal to L, approximately equal to L. Now what we will do is we will take the help of the concept of subsequence. Means what? Let us gather all terms of this kind, means x times x raised to n. Sequence is x raised to n already, which we call as s. And if I multiply all the terms by a constant x, then I get another sequence which is known as s dash. So it's a subsequence of original s, and this will also converge to c times, I mean x times L. A multiple of a convergent sequence converges to the same multiple of the limit. This is our theorem. So here again we will use the same. S dash is a subsequence of s. So s dash will have the same limit as that of s. Means x into L will be equal to L. So rearranging the terms and solving it, what we get, L times 1 minus x will be 0. But we are sure that x is positive and is smaller than 1. So 1 minus x cannot be 0. So what must be 0 is L. So we got L to be 0. I would like to once again revisit the same concept. So let us go here. Just see, if suppose our x is half, as we have already noted, if we take x equal to half, what happens? The very first term we have is half, next term is 1 by 4, next term is 1 by 8, on we go with 1 by 16, next is 1 by 32, and so on. So near about 5 terms I have listed here just to make it clear to you. What this sequence talks about, this is s equal to, the general term is half raised to n, or I can call it as 1 by 2 raised to n. Let me go with half. So half raised to n, and this sequence can be expanded as half, 1 by 4, 1 by 8, 1 by 16, 1 by 32, and so on. Now instead, if I go with another sequence, s dash, and I say this sequence contains half raised to n plus 1. Hope you are following. I am taking half raised to n plus 1, and as usual my n begins with 1. So it is 1 to infinity. Here also let me write the subscript. Yeah, and super. Sure. So what this will have, for n equal to 1, this will be half raised to 1 plus 1, meaning half raised to 2, which is 1 by 4. If I go with n equal to 2, I will get half cube, meaning 1 by 8. Next term will be certainly 1 by 16. Next term, fourth term, put n equal to 4, it is half raised to 5, which gives us 1 by 32, and so on. So what we mean, all the terms after half, they are enclosed in this bracket excluding half. What I mean is, s dash is a subsequence of s, and this subsequence is also having the same kind of property. So it is again convergent. We all know subsequence of a convergent sequence is also convergent and converges to the same limit. So this concept we have used while proving this. What we mean here, x into s is equal to x into x raised to n is the same concept that we observed here. This was half times half raised to n. So every term here is getting multiplied by half again. So we got this subsequence, and certainly the limit of the sequence is same as the upper one, same as the parent sequence. Alright. So once again we observe that if our x is a positive fraction, positive proper fraction, then the sequence of the nth degrees of that x is convergent and converges to 0 and nothing else. Now going to the next theorem. If x happens to be greater than 1, then what happens? This we mean to say. So the next theorem says, if 1 less than x less than infinity, then the sequence of x raised to n, the powers of x, diverges to infinity. This we mean to prove. Let us consider the sequence as which contains terms x raised to n, and the condition of x is greater than 1. So obviously the same kind of thing we are going to watch, whether it is monotone or not. So let us go to x raised to n plus 1, the next term. It is x times x raised to n, but we know that x is greater than 1. Let us see. What we know is 1 less than x. Now both sides let us multiply by x raised to n, and we know x is positive because it is already greater than 1. So I multiply by x raised to n, so this side is x raised to n, and here I am getting x raised to n plus 1. What we mean by this? The coming term is greater than the previous term, meaning the sequence is going on increasing. We can watch here 1 less than x square less than and so on, less than x raised to n, less than x raised to n plus 1. This is what is suggested from this particular statement. So certainly the sequence is a monotone increasing sequence. Now monotone increasing sequence, is it bounded above? So this kind of thing, you cannot find any m which will bind this. So S is not bounded above. And we know a monotone increasing sequence which is not bounded above diverges to infinity. So this sequence has to diverge to infinity. Now let us see why it is not bounded above. Is it surely not bounded above? This we mean to say. So let us try for this. If it is bounded above, then what will happen? If the sequence is bounded above, the nth term will have limit L. So sure, the next term will also go to L only. So Sn plus 1 will also go to L. Now what is Sn plus 1? Sn plus 1 is nothing but, you are calling it as L, and it is nothing but x raised to n plus 1, which we already bifurcated as x into x raised to n. So we can call it as what? Xn to L, because after certain finitely many terms, Sn will be L itself. So again we are reaching to the same kind of equality. L is equal to XL. So let me take L common. L minus XL, and this is going to be 0. If L taken common, inside we are left with 1 minus x. And as we know, x is already greater than 1. So this cannot be 0. 1 minus x cannot be 0. What is 0 is L. So if we say it is bounded above, it will mean to say that it is bounded above by 0. Sn is going to L, it is bounded, and we are saying the n plus 1th term is going to 0. How is it possible? because the terms are increasing terms, all of them they are greater than 1, so saying that it goes to 0 will be absurd. So this sequence is not bounded above, and that's why it diverges to infinity. So we got two kinds of results, very important results for us. If we are dealing with a sequence of powers of terms and the base x is a positive fraction, surely it goes to 0. But if the base is greater than 1, then it diverges, the sequence diverges to infinity. So both the results are quite important. Now let us try to go for the next term, next sequence. If S is a sequence, the terms we are denoting as Sn, sequence of real numbers converging to non-zero real number m. Wait a minute. Non-zero real number m, then the sequence t equal to 1 by Sn converges to 1 by m. So let us see what actually we mean here. We are handling, already we have S as a sequence Sn. Don't know what kind of terms it does contain, but what is given to us, the sequence of real numbers converges to a non-zero real number m. So Sn is a converging sequence and it converges to m, but for sure this constant value m is a non-zero value. 1 is non-zero means 1 upon m should exist. So 1 upon m exists, this is the guarantee, because m is non-zero. What we want to prove, if we take the sequence of reciprocals 1 by Sn, then 1 by Sn will go to 1 by m. This we mean to prove here. Certainly whenever we are handling 1 by Sn, we should guarantee that this Sn is not going to 0. Otherwise this 1 by Sn will not exist. It will not be a real number with us. So the terms are non-zero terms of the sequence, and m is also a non-zero one. Otherwise this will not hold. So for example, for short example, let us go with our favorite sequence 1 by n. You know, for n equal to 1, 1 by 1 is 1. Next term will be half. Next term will be 1/3. We all know. And so on. 1 by n. And so on. And surely this sequence goes to 0. So for such kind of sequences, this theorem will not work. We need to guarantee that the limit is a non-zero limit. Then only we will discuss of this theorem. Hope the concept is very clear. In this case, what is going to happen if I go with the reciprocals? The reciprocal of 1 is 1, reciprocal of half is 2, reciprocal of 1/3 is 3, reciprocal of 1 by n is n, and so on. Means we are dealing with the sequence of natural numbers, and the sequence of natural numbers, you know, is not bounded above and diverges to infinity. So such kind of sequences are not taken under this particular lemma. Which kind of things we handle? those for which the limit is non-zero limit. Okay, let us go to the statement. So here, if S is the sequence of essence of real numbers which converge to a non-zero real number m, then the sequence of the reciprocals of those terms will converge to 1 by m. This we mean to say here. Let us go with the proof. Okay, so let us go with the proof. So you are given convergent sequence S which converges to M, and what we want to show is the sequence T of 1 by Sn, the reciprocals of the terms, converges to 1 over m, converges to 1 over m, not m, it is 1 over m. Okay, now as m is non-zero, m is either positive or negative, so we have to deal with the cases. Whatever we are going to prove for positive, same can be taken for negative, because in that case it will be minus 1 by Sn kind of terms. It will go to minus 1 by m. So to show for any given epsilon greater than 0, there is n in capital I. Capital I is the set of positive integers such that the difference between the nth term and 1 by m is smaller than epsilon for all n greater than or equal to capital N. Meaning, once we cross this n finitely many terms, the remaining infinite number of terms, they are gathering near this 1 by m. This we mean to say. So if I simplify this particular 1 by Sn minus 1 by m, so let us go here, actually let us solve it. So what happens if I handle 1 by Sn minus 1 by m? What actually do I need? This let us see. So this is going to be inside modulus. We are dealing with the fractions. This is m times Sn, and this is m minus Sn. So we can call the same as modulus of Sn minus m, because this kind of terminology is familiar to us. And in the denominator we all know that m is positive, so can be taken out of the modulus. M can be taken out of the modulus, and I just want to deal with modulus of Sn. So we want this particular to be less than epsilon. So let us see how to adjust. So we have to find out this capital N such that after crossing this n, we will get this particular term to be smaller than epsilon. Alright, let us go one by one. Now we know that the original sequence Sn is convergent sequence. So for any given epsilon, there will be some natural number. After crossing that natural number, all the terms will go close to this m. This is what we mean by this particular statement. So in this case, let us take this epsilon to be m by 2. We can handle any epsilon. So let us, for the time being, call this particular epsilon as m by 2, half the m. So what is going to happen? The difference between Sn and m is smaller than epsilon, means m by 2, and after crossing that particular n. let us once again revisit. We know Sn is convergent. So for any given epsilon, we will be able to get a natural number. After crossing that natural number, all the terms of the sequence will be close to m. This is what we mean. Here we have taken epsilon equal to m by 2. And for that epsilon we say there is some natural number. We are naming it as n1, such that mod of Sn minus m is smaller than m by 2 for all n greater or equal n1. Now let us try to simplify this. This is the inequality. So what we observe here, minus m by 2 less than Sn minus m less than m by 2. All of us know this very well. If suppose we are handling mod x less than c, how do we handle such kind of terms? We say this statement is equivalent to minus c less than x less than c, meaning the value in the modulus sign lies between minus of c to plus of c. This is what we have handled. We are saying this Sn minus m lies between minus m by 2 to plus m by 2. When this is true, for all n which cross n1, which are greater than n1. Okay. Now let us add this m throughout. So what happens? M minus m by 2 is less than Sn less than m plus m by 2. What we mean by this? This m minus m by 2 is simply m by 2. So all the terms Sn are going beyond this m by 2. This is what we mean. So m minus m by 2 is smaller than Sn, means m by 2 is smaller than Sn. This fact we are going to make use here. So let us highlight. Alright. Now let us go next. We have taken care of this mod Sn here, saying this mod Sn is greater than m by 2. As you know, we want to handle the mod Sn in the denominator. When we are talking about denominator, we have to take care of such kind of terms. Alright. Now we are going ahead. If we take epsilon as m square into epsilon by 2, m square into epsilon by 2, then for this epsilon also we will have some natural number n2 in I, such that modulus of Sn minus m is less than this particular value. So the difference between the nth term and m is smaller than this particular epsilon value, as we are taking once this n crosses n2. Now what we will do is we will take the maximum of n1 and n2. We will call it as n. If n is maximum of these, it's very sure that once you cross this n, both the inequalities hold, both kind of statements. Yes. So for all n greater or equal n, we consider this difference mod of 1 over Sn minus 1 over m. Already we have simplified this. So this is mod of Sn minus m upon mod of Sn into m. And let us now simplify this particular. What do I really get over here? So mod of Sn minus m is, we have stated here. So we can see this is mod of Sn minus m, and in the denominator we are handling mod of Sn times m. So it is surely mod of Sn into capital M. Now I know that the numerator is smaller than m square into epsilon upon 2, and the denominator we know gives us m by 2 into m. So what happens is, this calculation give us 2 epsilon. If we cancel them, what we are getting is epsilon. So after crossing this capital N, we find that this particular term, and this is nothing but the expansion of what? This is nothing but mod of 1 over Sn minus 1 over m. So this difference is made smaller than epsilon once you cross this n, capital N. Thus the sequence of reciprocals converges to the reciprocal of the limit. I repeat, the sequence of reciprocals converges to the reciprocal of the limit. So up till now we have seen operations on convergent sequences. Let us just try to recollect whatever we have talked of. So up till now the results we have taken are if you are having Sn, a sequence which is converging to L, and sequence Tn converging to M, then if we talk about the sequence of sum, I mean term-wise addition, Sn plus Tn, then we have seen this sequence converges to the sum of the limits L plus M. It obeys the algebra. If we are handling Sn minus Tn, this also we have already seen converges to L minus M. Then the next term comes as, if you are having some real number in hand C and multiplied to then all the terms Csn, so scalar multiple of the sequence goes to the scalar multiple of the limit C times L. This already we have seen. One more thing we have seen, if we handle Sn square, the sequence of squares of those terms which are converging to L, surely this converges to L square. This is also proved. One more thing, if we take term-wise product, means Sn into Tn, and we have seen that it goes to L into M. It goes to L into M. And just now we have seen, if we are having 1 by Sn, just a minute. If we have the sequence of reciprocals 1 by Sn, then that sequence also goes to 1 by M. It was M there, so here let me have 1 by L, because Sn is converging to L. Only one thing we have to guarantee, that L is non-zero number. If L happens to be a non-zero number, then only we will be able to find out 1 by L. That's the only requirement we have. Means those sequences which converge to 0, we cannot handle their reciprocals. That's the thing. And we have seen with the help of example, that example was diverging to infinity. So this is what all we have. So here we handled the addition of the sequences, subtraction, I mean difference of the sequences, square of the sequence, product of the sequences, scalar multiple of a sequence, and reciprocals of the sequences. Now what more to come? We want to handle the sequence of the type Sn upon Tn. We want to handle the sequence Sn upon Tn, means we are handling term-wise quotient of the sequence, and short we want to prove that it converges to L upon M. So this is our upcoming target. We want to show that this sequence converges to L upon M. If anything is there, please chat in the box. Go in the chat box. So let's have a poll here. Let's have a poll. If x equal to 3.2, then the sequence curly bracket x raised to n dot. Options are converges to 0, diverges to infinity, next option is diverges to minus infinity, oscillates. Poll has started. Yes, come up please. Be little fast. Okay, I end the poll and I go with the majority. 83% are saying that the sequence diverges to infinity. So it's a good thing. Let us see how it happens. Our x is 3.2. It's but sure that it is greater than 1, and whenever x is greater than 1, the sequences of the pattern x raised to n, diverge to infinity. There is no question of getting minus sign because all the terms are positive, the powers are going to be positive. There is no question of oscillation because no term will come back. All the terms are going on increasing. And the very important thing is if all the terms are greater than 1, how can they come to 0? So none of them will converge to 0. So the sequence will short go to infinity. Alright, let's have one more. So another poll is on your screen. It says if x is 0.99, then the sequence converges to 0. Be fast. The value of x is given to be 0.99 and we are taking the sequence of the powers of x. Will the sequence converge? Will it converge to 0? Yes, I end the poll and everyone has given the correct answer. The sequence converges to 0. It's short because x was less than, x was given to be 0.99. How close it is to 1 doesn't matter, but it is smaller than 1 matters a lot. This being smaller than 1, the sequence has to converge. X raised to n will surely converge to 0. Alright. One more question I would like to pose. the sequence curly bracket n plus 1 upon n cube so how will it be? Converges to 3 converges to 0 diverges to infinity or oscillates. The question says it is a sequence of the terms like n plus 1 upon n cube, and the options are it converges to 3, converges to 0, diverges to infinity or oscillates. Okay, 83% of them they are correct. Let us see how. I end the poll and let us go ahead with this example. We are having the numerator as n plus 1 and denominator is n cube. So as you all know, while taking limit as n tends to infinity, what we do? We take the largest power of n common and try to operate on it. So limit n tends to infinity, as you know, from the numerator I will be getting only n common. In the bracket I am left with 1 plus 1 over n. In the denominator there is single term n cube, and let us cancel this n. If I cancel, I am left here with n square in the denominator. So how it has turned? This is limit n tends to infinity. There is 1 by n square multiplied by 1 plus 1 by n, and whenever n goes to infinity we are all sure that 1 by n goes to 0, 1 by n square also goes to 0, so the ultimate result is going to 0. So it's but natural that the sequence will converge to 0. It's a good try, very good. And one more thing, n's are all natural, and if they are natural, there is no minus sign over there is no simplification going to negative side, so all the terms are sure short positive, so there is no question of oscillation over here, no term will come back, so there is no oscillation. If you want, you can try with taking values to n. If I talk about n equal to 1, my first term is going to be 1 plus 1 upon 1 cube, meaning my first term is 2. What is the second term? 2 plus 1, and upon 2 cube you will have 2 cube is 8, so 3 by 8, so this is 3 by 8. You can see the first term was 2 and you jumped to 3 by 8 down. It's a fraction. Now let us go to the third term, 3 plus 1, and upon you have 3 cube. 3 cube is 27. So the value is 4 upon 27. It is still smaller than that. So you can visualize using decimal representation how rapidly it is going down. It is going down towards 0. It is being a fraction, and you know n is positive, so there are no chances for this n to cross this 0 and go to the negative side. It will never be negative, so it will be positive but rapidly falling down, so it goes to 0. That's the thing. So I think it was quite fine. Let's have one more kind of question. Let's have one more poll. The sequence curly bracket numerator 2n cube plus n plus 1 bracket close upon n cube. Yes. So what will happen to this sequence? I would like to reread it. The numerator is 2n cube plus n plus 1 and denominator is n cube. What will happen? Converges to 2 converges to 0, diverges to infinity. So let's have diverges to infinity, and yes, I would like to go with oscillates. I reread the question. The sequence to n cube plus n plus 1 upon n cube. Yes, the majority is correct. The sequence converges to 2. Let us see how. Let us see how. So our terms are 2n cube plus n plus 1 and divided by n cube, and we want to see what happens when n goes to infinity. So let's apply limit on it. Limit n tends to infinity. So let us take the largest power common. Limit n tends to infinity. From the numerator I'll have n cube out. Inside I'm left with 2 plus 1 over n square and plus 1 over n cube. And in the denominator I'm having single term n cube. N cube gets cancelled, and if I apply the limit, I'm having 2 plus 0, so value is 2. So that's quite correct that the sequence is converging to 2. So it's a very good try, all of you. So hope this will be fruitful. Just keep studying. Bye.